Rossi-Hansberg from the economics department. He's a friend of Mansueto, and we finally got him over here to give a talk. And he, as so many of our speakers, this is somebody I know, and then I learned so much about them by reading their bio to introduce them. And this could be a very long introduction if I read all of his honors. So I'm just going to give you some key highlights. But Esteban's, as I said, a professor in the economics department. Prior to that, well, first of all, he got his PhD here, so he started off on a good foot. He was at Princeton for, 15 years, at Stanford for a couple of years as well. And then he's been back here since 2021. He's an associate of the NBER, many other places. He's the co-director of the International Economics and Economic Geography Initiative over at BFI, the Becker-Friedman Institute. He's an editor of the Journal of Political Economy. He specializes in international trade, regional and urban economics, and as well as the structure of cities. So many interesting papers on cities. I won't try to go through a list of them. He's received many honors, including the Alfred Sloan Research Fellowship, the August Loesch Prize, the Jeffrey Hewings Award. He is an elected fellow of the Econometric Society. He won the Robert Lucas Prize. And he was elected to the American Academy of Arts and Sciences in 2022, which was a very, very good year. And without further ado, he's going to come to us and talk about his paper on local GDP estimates from around the world. Esteban, the floor is yours. Welcome. Thank you.
Chris was elected to Academy the same year as me. Okay, so thanks for having me. It's great to be here. I've done a lot of work on urban economics, and this talk is a little bit not out of character, I would say, in terms of the type of work that I do. It's mostly very structural, trying to think about equilibrium structures of cities and the distribution of economic activity more widely, and then quantifying them to think about like policy and policy exercises and factual exercises in general. But in doing that, all that work that I've been doing on the structures and in the effort to inform these structures with kind of detailed data on kind of local economic activity, one of the challenges that we have is that we need local measures of GDP or some measure of the level of economic activity in a location to inform these models so that we can quantify them and then do whatever exercise we want to do with the model. And so one of the issues that we face throughout is that there is not a lot of data on local GDP, and that we need to we need to get it, and in particular we want to get it in a way that is uniform across units, potentially uniform across the different locations that the analysis is trying to think about. And in many cases, we're doing exercises where we're trying to think about the distribution of economic activity overall in the world. And so we need units that are consistent across all areas in the world. And so that's the effort. The effort is, well, can we generate data sets of local GDP everywhere in the world? Right? And so that's the goal of this. And like I said, these are in principle valuable, both if you want to do kind of reduced form empirical analysis, but also if you want to do like a spatial structural analysis, which is kind of what I was referring to before. Okay, and so there's some efforts out there that have tried to do this before us, and we use them all in the sense that we use the data that they've generated in the past to do the type of structural work that I was referring to. But the problem is that they've either become outdated, or they've are not using the latest techniques, or they are very kind of specific to a particular area of the world, which cannot be really used more broadly everywhere. And so we want to kind of circumvent that. I mean, the most used perhaps of these is the one that Will Nordhaus generated which is called GECON, which is a data set of local GDP at the 1 degree latitude by 1 degree longitude resolution. And so that has been used a lot. I've used a lot that in my work as well. But last year this was generated with 2005 to getting all. And then it's not, population plays a crucial role in this. It's very, reliant on the data on population. It's very kind of proportional to population. And so, it's not really capturing the extent to which economic activity varies relative to population counts in a given location. Then there is this paper by Henderson, Story Garden, Whale, that uses night lights. And, that's clearly not the only paper that uses night lights. There's a whole literature that has used night lights as some sort of measure of local economic activity. And the key advantage of night lights is that you get them uniformly across regions in the world. And so everything that is remote sensing, night lights being an example of that, for us is great, right? Why? Because it's exactly uniform, right? I mean, the way in which you collect it in the middle of Africa is the same as the way you collect it in the middle of the US. And so for us, that's kind of really helpful. Well, if you get administrative data, that's just not true. Yeah.
So, I mean, the fact that seems like it made sense definitely like in 2012, but the fact that there's so much effort, to use intelligence technology to turn off and on night lights, might actually decrease its correlation with energy relevant expenditures, right? So if you're spending more money basically turning off the lights smartly at the right time in the right place, then you should see a lot less covered, even though there's more resource that goes into
right. And so we're gonna part of exactly the effort that we're gonna try to do here is use whatever uniform measure of night lights we have, which of course is gonna, I agree, it's gonna mean different things potentially across different areas of the world, but the measurement itself is consistent, right? And so we're gonna use night lights. We're gonna use all other remote sensing data that allows us to try to look at interaction that maybe, if we do it well enough, can capture some of the things that you're talking about. But it used to be the case that also these like nightlight data, etc., had some other issues there in terms of saturation, sensor inconsistency, that sensors kind of got old, and so it was kind of hard to compare across time, etc. A lot of that has been solved with the new nightlight data sets that we're gonna use. So we think kind of it's relatively better than this. And then, there's work that is more consistent with what we're doing, but it's kind of for particular areas in the world. In this case, for example, is for the US. And so, overall, we're still lacking this kind of comprehensive, up-to-date local GDP data. This is what this work is trying to do. And so, what are we gonna do? Is we're gonna develop some statistical model of local GDP. The emphasis is going to be on shares, in the sense that we're going to try to predict the share of economic activity in an economic unit, say a country, and then we're going to scale it up with actual, statistical agency measures of the level of GDP. So if I want to know total GDP in a given cell in the US, I'm gonna have a method that explains, well, this cell has a certain share of total GDP in the US economy, and then I'm gonna scale it with, official measures of the total GDP in that economy. And so by construction, I'm always matching the level that the World Bank tells me is the level of GDP in a given location. Okay, so this is only about the distribution of economic activity within, it's not about the level of economic activity overall in a country. We want to be able to. Now, the other big challenge here is that if in setting up these models and training these models, etc., you need actual local GDP data to train the model. And so the question is, well, what's the level of resolution of these of this data? But also, we're going to be training in certain areas of the world, not in every area of the world, because exactly the whole problem is that we don't have the training data everywhere in the world. And so we have exactly the problem of your comment, which is, you're training here, but then you're kind of extrapolating there. And so we wanted to be kind of robust to that, right? I mean, that we're training in one region, but then when we go and test it somewhere else, it works well. And then the other thing that we want is that, whenever something happens in the economy and we see dynamics, kind of local dynamics of economic activity in response to some shock, that the method kind of captures that well, right? And so that the time series properties, if you will, or the dynamic properties of the measurement is good, okay? And so that we're gonna kind of focus quite a bit on that. And so we're gonna use high resolution data on nightlights, population, land use, CO2 emissions, ruggedness, and some measures. This is a NASA generated measure of net primary productivity, which is some measure of local vegetation. We're gonna combine them with random forest, which is just a way to estimate the coefficients of the model, and in a way that is robust to overfitting. And then like I said before, we're going to be estimating this function f that is going to give us the GDP share of a particular cell in a particular country as a function of these variables plus some error and a potentially non-linear function of these variables. Okay, so that's the goal. That's what we're trying to do. And so let me give you a little bit more of the details of this. And by the way, to jump in with questions if you have any, right? Okay, so the nightlights data that we're going to use is this black marble data. It's provided at 500-meter resolution. We're going to aggregate quite a bit more than that in order to generate this. And again, why are we aggregating quite more than that? Because at the end of the day, the GDP measures that we have to train the model are much more aggregated than that. And so we're going to have to, so that's the compromise that ultimately we're going to be making. I'm going to show you three results for three different resolutions. One is going to be the 1 degree by 1 degree, similar to the NorCal data set that I was describing before. One that is at a half degree and one that is in a quarter of a degree. Okay, so those are going to be the three levels at which we're going to be operating.
So you're just doing different resolutions, or are you building like kernels based on the higher resolution to apply to the lower resolution, right? Because if you kind of, imagine you've got a Gaussian kernel, you can basically allow or facilitate, kind of broad mixing across areas, but you're still going to have density at actually a very specific high dimensional point. So kind of both. I'm just trying to think how. So
the model that we're going to do in what I'm going to show you today is we're going to do it at three different levels of resolution. We're just going to have the model at that level. We're not going to combine the model, which potentially you can do. But I'll show you the problem that we have in terms of attributing GDP at the cell level, which at the end of the day, you have to attribute in some way. And that already kind of limits the extent to which you can go to finer resolutions than this, because you are essentially just using population to attribute the local measures of GDP that you have across finer latitudes than that.
That's right. I just mean that the boundaries are going to be different because you've got very specific administrative structures, that emit a local GDP. And so if you were exploiting fine grained, so it's really just at the boundary of the low resolution GDP information that you want.
No, I see what you mean.
Anyway.
Okay, so this black marble nightlights data, solve some of these issues that I was mentioning before, gas flaring, noise and temporary lights, consistent satellite sensors, etc. So we're gonna just take all of that from them. Then there is this land use data that identifies different uses based on images of urban, cropland, forest, and so on. and then we're gonna use this measure of net primary productivity. All of these are, like I said, very kind of detailed, but we're gonna aggregate quite a bit more than the 500 meter resolution. This last one is the one that has been used the least to do this. It's particularly useful for areas that are kind of low density areas that have, mostly agricultural production, not other forms. So that's the remote sensing data. Then there's data that already comes from models, so that there's some processing of data that leads to some estimation of these quantities by the unit that provides them. In general, are more aggregated than what we're doing. So that's the basic population data that comes from Landscan. That relies also on some processing of the data, but it also relies on local accounts and official local data, which is a lot more accurate than the GDP data that is provided in general for these things. Then there's CO2 emissions, and then terrain ruggedness. We're gonna use all of that. Okay, and finally there's the GDP. Like I said, we're gonna scale everything to national GDP, which comes mostly from the World Bank or a few other sources. Then we have state level GDP for many countries, as you see there. Mostly it's developed countries, but we try to add a bunch of developing countries to make it, to make sure that we're kind of doing a good job also in areas of the world, which are the areas that have less data. And that's particularly a concern when we go to the most local level. So the OECD has pretty good statistics on that. But then we have to go to other work that has kind of collected by hand data for kind of countries that are kind of developing countries. And so, this is, ultimately, it's not like super important for the results that I'm going to show you, but we thought it was important to bring this in to make sure, again, that we don't generate like a developed country kind of measurement of these things, and then we're attributing to Africa something that has nothing to do with Africa, right? And so that was the concern. Okay, so here is like the typical processing of data that we're going to do. So think about like a map, has a bunch of counties here in the US, say, and then we want to have an estimate of GDP in the square. That's, say, the 1 degree by 1 degree. This is an actual cell. And then what are we going to do? What we're going to do is we're going to approximate the share of GDP in this cell, or the level of GDP in the cell, before we divide by total GDP in the country, by doing like the average, weighted average by population. So we calculate output per worker in each one of these cells, and then multiply by, or in the part of those cells that is inside this square, and then we use the population as a weight for that output per worker. Okay, so this is attributing to this little piece here, the output per worker of this, right, to the share of people that are in this area relative to these other areas. Okay, so that's the calculation that we're doing there. So essentially, just average with population weight. That's what we're doing for GDP. And then for all these other measures that we have, including night light and emissions and everything else, we're attributing according to area. So we have some measure X of the value in each one of the units available. In general, these are very kind of detailed units. As I show you, those are like the 500 meter units that we were talking about. And then we have the area that is inside of that unit, that is inside our square. And then we're gonna sum over that. Okay, so it's we're weighting by the area in that pixel that is within our kind of bigger 1 degree by 1 degree or whatever measure we are using. Okay, and so that applies to pretty much everything. And so that gives us a measure of these local GDP. It gives us a measure of the share of all these other variables in each one of the squares. And so that's going to constitute the baseline data that we're going to use to do the estimation. Okay.
Esteban, just as like a point of reference, like how many cells are there, say, in the continental United States at your different levels? I'm trying to get a sense of how big or small it is.
Yeah, I mean the 1 degree by 1 degree is there's like 17,000 cells that have some land in them. I mean the world as a whole is 60 by 360, right? But there's about 17,000 that have some land in them, and then you know, half a degree is times 4, 1/4 of that is times 8, right? Times 60. Yeah. So many cells, right? I mean, and now, of course, once you go to, if I want to say study like a city, I mean, I'll show you the maps for the 1 degree in a minute. Then you want to go to a finer resolution than 1 degree, because 1 degree is going to be like the city and maybe like a couple of surrounding cells, but that's it, right? If you want to go more, a little bit more detailed than that, if you want to analyze a specific region, then you want to go at least to the 0.25, and that's what we're doing, because it allows you, it gives us a little bit more. But the problem, and this is the problem that I was referring to before, is that, you know, in a bunch of cases, I mean, this is a case that is data rich, right? It's a case that is data rich in the sense that these areas are small, right? And the square is large. And so in some sense, the going to a 0.25 degree here, you know, is not a problem, because you still have a lot of information about that, right? The problem is more when you go to when these areas are bigger, which happens, for example, when you only have state data in a country, and so then you can divide it, but then there is no real information about local GDP except for population counts, right? All those cells would have exactly the same GDP adjusted for population counts. And so then if you go very fine, you really don't have any information about it. But then when you go to other measures like night lights, etc., these cells are gonna look different. And so that's gonna constitute a problem. And so really, the key constraining part of all of this is the GDP data, and kind of what's the resolution that we have for GDP, for the GDP data. Okay, and then we're going to combine this with the random forest model. The random forest has a bunch of parameters that you have to tune, in particular parameters related to terminal node size and number of trees, etc. We're going to choose all of that to improve the out-of-sample logarithmic growth rate of GDP prediction. So what that means is our focus for choosing those parameters is to try to optimize on how well the model does on the growth, right? Log growth in these different areas. Okay, because in general, it's kind of relatively, or it's much simpler in general to get the levels right, to get the dynamics of these cells over time right. It's more complicated. And so that's what this is trying. We're trying to kind of optimize on that. Okay, and so this is okay. So that's the kind of implementation of all of this. Then you know, we run it, and then we run it for the 1 degree, half a degree, and 1/4 of a degree models, as I mentioned. And these are the basic baseline results, or the kind of accuracy, if you will, of the baseline results. So this is the cross-validated, meaning, you know, you run it, and then you have a set of countries that you leave out, and the set of countries that you leave out is random, and then you're checking your R square, how well you do in the countries that you're leaving out, right, for the testing, okay? So this is all in some sense out of sample testing. And so you can see that this does really well, right? I mean, in levels. So the R square, so focus on the old one. The other one shows you for developed and developing countries. You can see for developing countries, we have less data, less granular data. So we're doing a little bit worse overall. I mean, all these numbers are extremely high. So in levels, we're doing really well. The criteria that we are optimizing the hyperparameters on, it's this. You know, if you do it on levels and you don't do it on this, the results don't change that much, but I mean, it's kind of a detail to mention. And then if you look at our squares here, in terms of growth rates, I mean, they're, well, much lower for sure, but we think kind of pretty successful, right? So what is this telling you? It's telling you, look, you know, now we have a model that can tell you kind of based on the characteristics of the cell, how much the GDP in that particular cell is growing, and it's getting that right kind of fairly accurately over time, and certainly right in terms of levels. And then the last part of the table here is showing you kind of the loading, kind of how relevant in some sense the different variables are. And so, not surprisingly, nightlights and population, but not only nightlights in urban areas in particular are very important, and then population, and then all the others, these other variables matter as well, but certainly not as much as this. And then there's of course all sorts of interactions, etc. The other thing that is kind of important to note is, look how these weights vary quite a bit depending on the specific resolution that we're talking about, right? So what variables are important in getting one resolution versus another don't necessarily have to be the same. The other thing that is kind of we think interesting is just these variables here matter a lot in terms of you know, the way that the model puts it in them. But if you only have those, right, the model performs way worse. So these other variables, even though you're not putting a lot of you know, weight on them, they improve the precision of the estimates quite a bit. So I have it. I'm not gonna click on it, but you know, it's there if you want to check them. If I were to click on this, the accuracy is it's a lot worse. And so there's something to gain from adding all these.
Can I ask just one question about that last slide?
Yeah.
So why is the 0.25 degree model so much better in the panel B, the R squared of the log, GDP and T minus? Yeah, those are all way better, right? Whereas if anything, they perform a bit worse in just the static GDP, and then all of the other importance variables are like you know, half as large.
I agree. So
because interactions are more important. Like,
right.
What's going on? Yeah.
So it's related to this issue that I was mentioning, that ultimately the target. So we're trying to explain local GDP, right? And local GDP, as I was mentioning before, it's partly calculated from population, right? We're using population weights to calculate it. Now, the finer the resolution, the more important the population variable is. That's what I was responding to Chris, right? And I'm using population too, right? I mean, as an explanatory variable.
Yeah.
So that issue becomes bigger and bigger. And in the limit, when I go to like that resolution where I don't have GDP at all, it would, you know, perform really well because I have that variable. Okay, so you can see. I mean, here it's a problem. It's not a huge problem yet, but part of the improvement that you see across columns here is exactly
It's the relative difference.
the fact that you have population, and population is kind of infecting in some sense your original measure of GDP that you're training on.
Yes.
So that's mostly it. All right, so that's this. Like I said, I mean, I think we're doing kind of much better than if you just use you just use nightlights data. One other thing that we do, well, you can see the different results depending on whether we use developed or developing countries, and then this weighted model here. The weighted model is at the end of the day what we're going to use, because we have a lot more data on the local level for developed countries than for developing countries, but we don't want the model to overweight the data for the developed countries. And so we're gonna re-weight towards the developing country data in order to make sure that the model kind of is representative for developing data, which is important. It's important for us. Okay. All right. So this is like an example. These are the 17,000 cells that I was mentioning before. The one thing that we're gonna do, see that there's a bunch of gray areas. So gray areas are areas, so this is particularly for 2019. The gray areas are areas where the population data that we're using, with very few people or 0 people, I think this map is for 0, in that cell. And so even though we can, in principle, generate a GDP measure for that cell through the model, I mean, the model would give us a specific share for that cell. We're censoring it at 0 because there's no people, and so the argument is if there's no people, you cannot produce anything, right? Now, in principle, I mean, in fact, we have it out there too. You can generate a number. And so to the extent that the population count is not that accurate, etc., this would give us an actual level of GDP in these areas. Now, in general, this is all going to be very close to 0 anyway, so it doesn't really matter that much. But if you want predictions on GDP in the gray cells, you can kind of generate that too. I mean, that's mostly kind of close to the North Pole, and then in parts of the Sahara here, apart from that, or parts of the deserts here in Australia, but apart from that, pretty much everything else is full. And the geography that you get is kind of the standard geography that you would predict from kind of population counts and knowing which countries are rich, etc. So this is GDP. That's GDP per capita. And again, here, everything is scaled at the country level. So the fact that, say, the US here, it's all in blue, while Mexico is in yellow, is just coming or partly coming from the fact that we know that the overall GDP of the US is, per capita GDP of the US is much higher than the per capita GDP of Mexico, and we're taking that from the official data. But there's still a lot of variation within the country. Say, look at Mexico, within the northern parts of Mexico and the southern parts of Mexico that are much poorer. And so that's the variation that the model is helpful in producing relative to the official data. Or or China, for example. So China is actually not used at all in this exercise because for most of this time, we don't really trust the local statistics produced by China. The later period, China has produced much better statistics, and we're going to use them. I'll show you something about China in a second. But again, you see a lot of variation there that the model is generating from this. And so these are big differences, right? This is what, like 6 or 7 points differences within these countries. Okay, and this is kind of why, in some sense, we focus on this GDP growth as one of the targets, because look at now the GDP growth, or if I go further, this is GDP per capita growth, right? Now, this is much less uniform in some sense within a country. Now, region by region, you have a lot of these variation within. And that tells you why it's so much harder in some sense to get those numbers and why those R squares, etc., that I was showing you were so much lower than in the case of levels, because levels, kind of those baseline GDP counts, etc., are much more indicative of what you see in those countries. So that's what makes it hard. Okay, so those maps are nice, but it's hard to make anything out of them. It's just a bunch of colors. So let me try to do a little bit of more with this. So the first thing is I wanna think about, well, to what extent, I mean, we were very concerned about this issue of population count and to what extent this is just like a measure of population, right? Because a lot out there is just like a scale measure of population. But if we want to inform studies that have this population and GDP as independent measures, because one, for example, governs, you know, the capacity to produce in a particular location, and the other governs how attractive is an area for individuals, right? We need independent measures of GDP and population. And so this effort is exactly about that. It's about generating that those independent measures. And if at the end of the day, the measure of local GDP is just scaling up population, then, you know, it doesn't satisfy, it's not useful for these purposes, or is not as useful for these purposes. So that's what this tries to show you. So on the x-axis, this is again the three resolutions. You can see that most of everything I'm going to say kind of holds for all of them. So on the x-axis, we have population. On the y-axis, we have this our measure of local GDP. And so and the dash red line is the 45-degree line. And so in principle, if these were these two things were 1-to-1, then no, sorry, did I say it right? This is not the 45-degree line. I think this is just the linear estimate of that relationship. And then we have the blue one, which is kind of a polynomial estimate of the relationship. And so there's a few things that I want to point in this graph. The first one is, okay, so this seems, you know, it's obviously very related. Population and GDP are related, as they should be, right? Or as we think they should be. But first of all, for a given level of population, look at the range of GDP measures that we're generating. So that range is about 7 log points. Now, 7 log points, I don't know how much you are familiar with thinking about log differences, but 7 log points is huge. It's a huge range, right? So that tells you, you know, within this, you are capturing correctly that within this population count, right, there's places that are very rich and there are places that are very poor. And the difference between this is, you know, 7 times, not 7 times, to the 7, right? And so that's a lot. It's big difference. So that's the first thing. The other thing that you see in this graph, it's a little bit harder to see, but certainly comes out in all these estimates, is that this is a convex, right? It's kind of upward sloping and it's curving up. And what do you make out of that? Is like this idea that, well, in fact, if you kind of look a little bit more careful, yes, it's convex here very clearly, less kind of at the bottom here. And so the convexity here is telling us something about the fact that, you know, places that are very big in terms of population also tend to be richer, right? So that kind of captures this idea of agglomeration effects once you look at all these cells. So overall, in the pattern of cells that you see in the world, you do see this convexity that says, in general, on average, places that have more population tend to be richer in terms of their GDP. And so that's where that convexity comes from. You can see that kind of relative to the linear trend. That's not quite the case at the bottom. So at the bottom, this is a little bit harder to see from this, but you see it in the polynomial. It's a little bit concave here. It starts concave and then kind of curves up. and so here you're seeing something more about, some sort of minimum scale to produce, right? That you need a certain, I mean, that's like the urbanization debate, for example, the fact that once you have that in order to do certain types of production, you need to do them in a city. It has to be denser. They're denser than certain levels. That's kind of not super strong, but it's a little bit there in the data. Okay, so that's just things that you kind of see a little bit when you analyze. And then the last thing I'll show you is a performance test with the COVID-19 pandemic. So like I told you before, we're not using China for any of this, but we're gonna go collect local data for China for 7 large provinces in China, and we're gonna kind of go to the city books and collect the data from there, right? So that's gonna give us a sample of Chinese GDP, local GDP levels. And then we're gonna contrast that during the COVID-19 period with the predictions of the model for China that we have, or the statistical model for China that we have. And so those are, on the x-axis here we have the true values, meaning the data value that we get. And then on the y-axis, we have the predicted values. And so you can see, again, there's levels in the top row, growth rates in the bottom row. So in levels, you do very well throughout, including the, pre-COVID period, COVID, and then post-COVID, which is like the last year that we have in the data. And, you do as well in one relative to the other. It doesn't matter too much which one you use. When you go to the growth rates, first of all, the performance goes down. We already knew that. But for the 2020 period and 21 period, you do actually quite well, even though, this is a shock. I mean, the whole reason we're doing this is because COVID is obviously something that had not happened before. So you can say, well, all the statistical analysis that you're doing, right, is kind of not going to really work that well once we have like this very specific new shock that we got, right? And so, and in particular in a country where you're not even using for sampling. And that kind of comes a little bit true in the fact that even though these two numbers the R squares here are fairly high, here you're doing really poorly in the pre-period, right? And so what's happening there? Now, the key when you do this thing and you say, well, you're doing poorly, is the key is this word, right? Whether this is you're comparing with the truth or not, right? Like the truth is what the local municipalities in China told us it was their GDP, right? That's what we're taking to be the truth. But we know that China did actually a big reform in standardizing all the statistics in 2019. It said that after the 2019, it standardized all the local statistics provided by the local government. And so in some sense, it's kind of once you understand that, is kind of this kind of makes more sense. I mean, in some sense, the model is actually capturing the fact that true data was not really true data in some sense. Now, if you go for, you can also do it for the world. You can check, pre-COVID and post-COVID. This is, I'm going to take the model, I'm going to train it up to 2019, and then I'm going to let 2020 and 21 be out of sample. And so again, in levels, you do great. In growth rates, you do worse, but still kind of fairly good throughout. Okay. And then the last thing I'll show you is this. So this is now, Wuhan is kind of where the whole thing started. So we're going to go get the data for Wuhan and then look at the time series of Wuhan compared to what the model gives us for the cells in which that are included in Wuhan. And so here we think that this is kind of, in some sense, a really nice show or test for the model, because it's really kind of asking, can you get for this particular area that got this shock a good prediction? And so you can see the actual versus the predicted. There's a little bit of the issue that I mentioned here before in terms of how well this is measured. For Wuhan, that is a relatively big area, etc., it's probably not such a huge deal, but it's still somewhat there. But the point is that the predicted part is kind of capturing all the ups and downs that you see in the data, even though the predicted model is not using Chinese GDP data at all, right? And so we think that's a nice test. All right, so that's all I got for you. So we think these measures that we're providing are useful. They can be used in all sorts of types of analysis. So I listed a bunch there, a little bit kind of including the stuff that we've been doing. And then the final thing I'll say is this. This is all public, the methodology papers, all the source data, all the data itself that is generated at the different resolutions for different kind of assumptions on the zero cells and all can be downloaded from the BFI data studio, and you can map it and you can play with it and you can do all sorts of things there. So if you're interested, go and play with it. Thank you. Yeah, questions, yes.
Yeah, this is fantastic. What are the plans for updating this, and how automated are the workflows to get these updates?
Yeah, great question. I should have mentioned this. The plan is to update it every year. And so our restriction is that there's the data products that I mentioned that we're using, those have to be released. The plan is for that they release them every 1 year. And once that happens, then we can do ours. It's not difficult to do that, and so we are planning to do it. It's not fully automated. We would prefer it to be fully automated for sure. We haven't fully automated it, but at this point, it's really kind of all the code and everything is there, and so the updating is not difficult. It's not difficult.
And the code for the workflows is open as well?
Yeah, everything's open. Yeah.
Are there differences in the prediction era in areas that are declining versus improving? So I imagine it's easier to predict growth than it is decline, because decline, buildings not getting demolished right away, et cetera, et cetera.
That's a great question. I don't know, but it's something that we can check, and it's an interesting thing to check, because I agree that on the downturn and on the upturn, you can have different. I mean, in particular with like the night lights are going to be much less informative on the way down than on the way up. That's a great question. We can definitely check that. Yeah.
Okay.
Sorry, I'll
Great
take you
work.
in a minute.
Okay, great work here. Very happy to see that. I've got a comment and also a question here as well. So the comment with regards to your model validation and the estimation about China's GDP using your model.
Yeah.
I think you can probably also compare your product with some work that they have done in China. I know a group of people I have collaborated from East China Normal University, Professor Bai Yu. They have also used nighttime light data. They have done a lot of work in this area, and they use that to estimate GDP in China under different levels. So it could be interesting whether they're using the statistical yearbook that might be not reliable, see how their work generated with the GDP compared to the results from normal.
That would be fantastic. So if you can send me the reference, etc., I would love to have it.
I'm more than happy to do that. Yeah.
Right. I mean, like there's a lot of people. I mean, one game in some sense that to some degree we're being pushed into trying to do, but we don't want to get into doing, is to try to make predictions about country GDP based on this, right? This methodology is not set up to do that. And so we don't think that we can do a great job in calculating country GDP. This is because the model is for shares. But to the extent that they've generated local GDP measures and we can contrast with them, we love that, yeah.
The other question I have is looking at Australia. I come from Australia, and then so I'm very interested in looking at that part. And then I can see actually a lot of variations across the continent, and then particularly in the city area, in the middle part of this the country. So from what I understand, you're talking about the population distribution, and I know that a lot of those areas in the central part actually have not many people at all.
I know.
So how does
So that's
that?
the red area there.
Yes, yes.
I mean, there's the red area there, and then you see the gray parts here, which are the parts where actually the data that we have says 0 people. So that I think is captured well. The part that is a little bit more complicated and that can introduce some error, and I think is a potential, that's kind of also part of the reason why we censored some of these areas, is that of course, if you have very few people there, right? And you take the ratio, that leads to huge potential fluctuations, right? And that also makes, for example, calculating growth rates really tricky because any sort of mismeasured of the number of people there changes the growth rates in GDP per capita dramatically, right? So that's in general a concern that mechanically is going to reduce the R squares of the growth rates a lot in those areas.
Yeah, great talk, Esteban. So I'm just wondering that for the figure you show, there are 7 log points between GDP within the pixels is the same population.
Yeah.
Is this comparing some neighborhood in Mumbai versus New York, or this is like comparing within the US?
This is the whole world.
The whole world.
So
Maybe you could do it
so
within a country.
this here, right? It is, yeah, this is the whole world. Variation for that given number of people per cell, right? So yes, so it's not, so that comparison is probably here, right? So yeah, so no, so this is not trying to, but you can do the equivalent graph for the US or for a specific area. I mean, this is just because we wanted to see, you know, are we kind of getting into the trap of G-econ where at the end of the day, most of the variation is GDP, or is these other variables really kind of carrying some weight in giving us independent variation in GDP from population? So that's, and so I think the answer from this is clearly yes, right? But you're right that one calculation that we could do is we could partial out the variation that is country level variation and redo this graph once we partial out the country level variation to look at the within country variation that we're explaining. And so that kind of is, that's kind of the point that I was trying to make when I was looking at GDP per capita, and I was kind of looking at the case of Mexico or some of these other cases. Then within country, within China, within Mexico, within the US, that's kind of what we're talking about. And that's still, in many cases, you see ranges of about 6, 7, even within countries. But it's smaller than what I showed in the other graph for sure. Yeah.
Thank you. I was wondering why you optimized the hyperparameters based on like GDP change over time, and whether you incorporated like that temporal aspect into like the actual loss function for the random forest, or was that just like the hyperparameters?
Yeah, so that's a great question. I mean, we do have some lags there, right? So the explanatory variables lagged in order to try to capture some of the dynamics there, and adding some of those lag variables actually helps. And then the reason is because it's kind of the big challenge is this. I mean, this is a much bigger challenge in terms of accuracy than the levels. And so everything that we can do in order to get the accuracy in the changes right helps a lot, right? It helps a lot when you wanna think about this to explain, for example, the type of things that he was saying on growth and etc. Right? So that was the hope. The hope is the model is worse on the time dimension. So let's choose things so as to get the best, most accurate model on that time dimension. Yes.
If this model goes to like 1 degree granularity, 0.5 degree granularity,
Yeah.
is it correct to think that the smaller you go, you will have more sort of spatial continuity in GDP or like change in GDP? And is there some way to incorporate this into the model where like you can't really have two cells next to each other, one going up 30%, one going down 20%, probably up pretty close.
Well, I mean, that's what you see here, right? I mean, that, you know, there's a lot of high growing versus low growing cells next to each other. Now, part of it is like, if you kind of squint a little bit, what you'll see is that problem is particularly accurate in areas that are not very dense.
Yeah.
Right? So if you look at, you know, the northern latitudes or close to the Sahara, on parts of the Amazon and places like that, you see a lot of the up and down. And that's the problem that I was mentioning before, which is like small differences in population, etc., that gives you big swings in those growth rates, right? And so then, I mean, then you can of course start saying, well, okay, so maybe, and these are all things to consider, maybe, you know, optimizing on log GDP growth is not what you want to do. What you want to do is optimize on level GDP growth, right? So then it's not going to be subject to this type of thing that I'm describing. But then, you know, the problem then is that there's going to be, you know, 1,000 cells in the world that really grow in levels, and those are going to drive everything. That would be the concern then, right? And so those are the concerns that you're balancing.
Yeah, I guess I had a thought along the lines of Peng Bin's, which is that kind of adjusting to the country level total is acting kind of like a country fixed effect of a lot of these regressions in terms of evaluating them after the fact and how contribute to it. So I think seeing within countries is interesting.
Yeah.
But actually I was thinking about, you know, there's this literature related to nighttime lights claiming that autocratic governments tend to overstate their GDP. In other words, if you fit a nighttime lights regression to the world and then you make predictions that autocratic areas tend to under or the overstate GDP.
But now you're pushing me to play the country level GDP.
Well, I guess I'm just kind of wondering, like, could you make these predictions for like one country at a time without holding the constraint that it must sum to the officials for this? And just see what the model would have told you the growth rate would be.
So to like, we haven't done that model with all the accumulated knowledge exposed, but that's the way we started. So we started by saying, let's get the levels. I mean, let's have a model of the levels at the cell and explain it with all of this. And those models tended to perform a lot worse than these models in terms of shares. And so that's why, you know, eventually we moved into the models, and this is the result of, you know, many iterations after moving into those models. Now, again, there may be accumulated knowledge that now if we were to apply it to the modeling levels, we could do better, maybe, but we haven't tried it. I mean, once we went into this direction, we kind of stayed in this direction. But I think there is definitely a project. I'm not sure that is my project, but it's a project that is about trying to do this type of methodology to try to see the extent to which people are misinterpreting or misrepresenting their GDP. Now, a key thing, of course, is that you need to take a stand on some countries and some regions that are not, right? Otherwise, the whole model is kind of impacted by the problem.
And I guess you're implicitly just have in mind that they're not misrepresenting shares, or like they may cook the books in terms of their aggregate GDP growth in some authoritarian country, but maybe not in terms of how it's distributed.
I think in general that's harder to answer. I think that's harder to do. Because it has to be kind of consistent. I mean, at least the optimization process to get that right is a little bit more complicated.
One quick question following up on Division's point. So you're using cells, but what substantively is actually the spatial unit that would make most sense in terms of local GDP production?
Right. So the data is all calculated the GDP data is all comes at whatever the local administrative unit is, whenever we have local GDP data. But the rest, the remote sensing data, it's all at this artificial unit. And so you can, I mean, we could build it into the whatever administrative units there are in the country. Now, for us, and this is probably more selfish than providing a generic data product for everyone, but for us, we don't. The models that we're writing down are models that are all cast in terms of this type of arbitrary cells, and so we want the data in those cells because that's what we can. That's the way we use the data, but aggregating up from say the 0.25 degree to whatever local administrative unit you have, using population as weights is very easy to do. So that kind of post-processing of the data is relatively simple.
All right, well, thank you again, Esteban.